Hello, my name is Anthony Pepitone, and today we'll be looking at Lab 2, Motion of a Falling Object. We will be discussing the purpose of this lab, preview of results, fundamental principles, some videos, code, models, and what it all means. The purpose of this lab is to measure the object's motion after it has fallen some height. We need to understand the momentum principle and Newton's second law in order to help us do that. Along with this, we will take into account gravity and drag and how they will each affect the object's overall motion. Before getting into the lab itself, a brief preview of the results should show us that the models do not exactly align with the observed data, but the model with gravity and drag is much more accurate to the observed data. Here, we can look at the fundamental principles and the equations we will need in order to better understand this lab. Firstly, we have Newton's second law, which states that F net is equal to ma. However, this could also be written as F net is equal to dp dt, or F net is equal to m times change in v over change in t. Along with this, we will need the net force of gravity plus drag for the model with the drag. Here we have gravitational force is equal to negative mg times j hat, and g is the constant 9.8. The drag force is going to be Fd is equal to negative b times v squared over v hat. We need to do the magnitude of v, for you cannot multiply a vector by a vector. Here we can look at our original video. And from this, we can tell that the system is the paper ball and the surroundings will be the earth and the air. Going deeper, we could plug the video in a tracker and collect some of the data. Here we have the initial conditions that the position is going to be around negative 4.687 times 10 to the negative 3 in the x direction and around 4.687 times 10 to the negative 3 in the y direction, along with a velocity of 0, and the time it takes for all of this to happen will be 4.67 seconds. Here we have two sets of code, which will give us two computational models to compare to the observed data we looked at earlier. On the left, the only gravity side has F net equal to W, which he defined as the equation for gravity. Due to this, the velocity is a linear downward slope. However, on the right, with gravity and drag, we could see that F net is defined as W plus Fd. Here W is the same, resulting in gravity, and Fd will be the code that lines up for the drag force. Because of this, we can see that the velocity begins to decrease as it goes downward. This is because the drag and gravity will allow it to reach terminal velocity. Here, we can look at the three sets of data which we have discussed earlier. The blue line being the observed data, the red dotted line being the model without drag, and the yellow line being the model with drag. At the origin, they all seem pretty close. However, as we continue to go down, the red line drops further because there's no resistance in the air. The yellow line, however, gets closer and closer to our actual observed, and this is because, in real life, the paper had drag along with the gravity. Some possible sources of error when looking at the observed graph could be that when plotting the points in Tracker, I was off in plotting on the center of mass points. Along with this, the camera or axes could have been tilted slightly, therefore changing the graph slightly. Now, what does it mean? Here, the terminal velocity is reached with the drag and gravity model due to the forces balancing out. Terminal velocity is when an object is no longer accelerating in the air, and this is a result of the drag force being equal to the force of gravity. If there's no drag force, such as the model with only gravity, then there will not be terminal velocity and it will continue to increase in speed. However, with drag, we can see that it begins to slow down, therefore reaching terminal velocity. Now, we could also look at what if an object was thrown down rather than just drop from rest. It would actually reach the same terminal velocity rather than increasing in speed. This is because the gravity force and the force of drag are going to be equal at some point no matter what. As you can see in the left compared to right, they both begin to slow down to the same point. However, since the one thrown down has an initial velocity of -2, it reaches this point quicker than the one that was not thrown and dropped from rest. Thank you for watching.